We're here at Grimm Audio in Veldhoven of all places. Well, it's next to Eindhoven. People probably know that from Philips. Next to me is Eelco Grimm.
Nice to be here.
Yeah, well, nice to be here again. We're going to talk about the MU2. And of course, we already reviewed it. You know what we said about it, and our viewers probably know what we said about it as well. But we wanted to go a little bit deeper in terms of the DAC technology, but we can't start with the MU2 immediately because there's also an MU1. And maybe you can explain the differences for the people that don't know the differences yet.
Okay. Well, the MU1, we introduced that about 4 or 5 years ago.
Yeah, something like that.
And you can see that as a Roon network bridge.
Yeah.
It has digital outputs on AES-EBU and SPDIF.
Yeah.
So it's meant to be connected to an external DA converter.
Yes.
And that DA converter can also be inside a loudspeaker, like with our LS1 loudspeaker system.
Yeah.
And so that's a perfect match, the MU1 with the LS1 system.
Yeah.
Now the beauty of the MU1 was in 2 factors. One is it has a very low jitter clock.
Yeah.
And so because we use AES-EBU and SPDIF, that clock quality is influencing the downstream DAC.
Yeah, because that's really important. That if you use AES, SPDIF, or no, not USB,
Toslink
maybe, then your source is master.
The source is master, and the signal is not just data, but also clock.
Exactly.
And there are professional options for sending the clock downstream, like with coax cables and word clock.
Yeah.
But that's not so common in hi-fi.
No.
So for hi-fi, the only option, so to say, to get the clock into your DAC and to have the DAC respond positively to an external high-quality clock, that's through AES-EBU and SPDIF.
Exactly.
And so the low jitter oscillator in the MU1 is one important factor. The other important factor is that we had very high quality upsampling in an FPGA chip format.
Yeah, yeah. So it's a big chip that you can let do stuff you want.
It's a very powerful computer, so to say, in a certain format.
Yeah.
The advantage of using that FPGA for high performance upsampling is that it kind of releases some of the labor that needs to be done inside a DAC chip to a high performance computer instead of the lower performance computer that's always in a DAC chip.
Yeah.
And we found out that the quality of that process has quite some impact on the sound quality. So that's the MU1.
Yeah.
And now
so just a streamer, no DAC. You can use any DAC you want.
Yeah.
It was combined a lot with Mola Mola, at least in the Netherlands.
Yeah, but many other DACs.
But you can use it for every DAC.
Absolutely.
You want. Yeah.
It's a great source for any DAC.
Yes.
And now the MU2 has been introduced, and the main difference, of course, is that we have our own DAC built in.
Own DAC,
it looks completely identical, except for a slightly different color of the control button on top. Yeah. Of course, the back is different, all kinds of different connectors, but essentially it's the same box.
Yeah.
It's also the same Roon core and the same computer for that, and largely also the same software that controls the whole system.
Yeah, because you use an industrial grade computer for the Roon core. It needs to be passively cooled.
Yes.
So that was one of the questions one of our readers has. Why no i7? Well, it's pretty hard to cool it passively.
Exactly.
And you don't need all that.
No, and the advantage of the current well, actually, when we developed the MU1, so let's say before 5 years ago, the power of the computers at the time was finally good enough to have a neat box with passive cooling that was powerful enough to run Roon.
Yes, exactly.
And so that was really, it wasn't possible much before that to do it like this.
No.
And so that concept is also used in the MU2.
Yes.
So it's the same on that side. But it doesn't stop there. So instead of converting the data that you get from a stream or from a local file into an AES stream downstream to a DAC, we have built the DAC internally into the same box.
Yeah.
And after the DAC, there's an analog preamplifier. So it has a volume control in the analog domain, relay-based, and there's analog inputs that don't need to be digitized to be volume controlled.
Yeah, we're going to talk about that later with Guido.
Right, but in essence, it's your full system in one box. There's the source, there's the DAC, there's the preamp, and you can connect all kinds of digital sources to the back, just as with the MU1, and you can connect to analog sources as well on AES, on XLR, I mean, and on RCA.
And there's an headphone amp.
And indeed, the output, output is not just for your amplifiers, but also for headphones.
Almost forgot that.
And the sound quality of that is also quite high, because that's the whole theme of the MU2. All the elements, we had the intention to get that at the highest possible level.
Read our review. We're not a hi-fi platform, of course. There are other far better platforms for hi-fi.
Yeah.
But we tested it with a Focal, and it is indeed a very high quality headphone amplifier. So we don't write about it that much. That's why we almost forgot it, but we need to mention it as well. Yeah. But we're going to discuss the preamp later. I'm really enthusiastic about the analog part of the MU2, and most people think only digitally about the MU2, but it's a pearl. But the DAC is so much different from other concepts. We use a NOS DAC as a reference. There are chip-based DACs that perform really well nowadays. And still you thought, you know what, we're going to build our own DAC.
Right. Yes, and the reason for that is that it gives you full control over all the aspects. Yeah, true. And that's really one of the things that you can find in all our designs. Yeah. We are somehow, this is our ultimate goal, to get control of all the aspects. In our mission, we say we want to build a full signal chain from the microphone all the way to the loudspeaker at home. Yeah. and that's a crazy idea, of course, but you can only be successful in that if you have knowledge of all the different steps that the signal will pass through, and not just in the boxes, but also what's happening inside. And, and that goes down to details like what's happening inside the DAC chip. Yeah. And now with the MU1, we already addressed one of the aspects that's inside the DAC chip, which
kind
is
of the pre-processing.
Upsampler. Yeah. And so then the next step, what's happening in a DAC, is the actual conversion itself. Yeah. And the conversion can take place in a couple of ways. You mentioned the NOS DAC, the non-oversampling DAC, and that's a DAC that has 16, 18 or 20, whatever levels that it can turn into analog at once. Yeah. So you have your digital sample that is equivalent to a certain voltage in the analog domain, and that sample is turned into an analog voltage in one go. Yeah. And that's a quite old technology. Yeah. It's been around for ages. Yeah. And the disadvantage of such a topology is that it will not just give you the audio domain signal, but it will give you images above that. So you will have a mirror image of the same audio signal, but then above the hearing threshold of 20 kilohertz. Yeah,
there's no filter.
So there will be a lot of high frequency mirrors since there's no filter. Yeah. So with the first DA converters from especially Sony, they applied an analog filter to get rid of that, because the electronics isn't very happy with those mirrors. Your ears can't hear them, but if the high frequency signal is offered to the amplifiers, they start to behave less linear. They will have more distortion and all that, and perhaps your tweeter is also not so happy with all that energy. So this is can be problematic, and that's if you don't filter like in the modern NOS DACs, that can be a problem in some of the hardware. So the NOS DAC performance is quite dependent on the amplifiers and the loudspeakers that you use with it.
Yeah.
And it's well known that with tube amps it goes pretty well because they are less sensitive to that kind of high frequency noise.
Yeah.
Now, this is not the most elegant way to turn a digital signal into analog. And there's also a problem that has been defined already in the early days of digital to analog conversion. That is, there's a linearity issue because it's very difficult to get all the voltages at the same resolution.
True.
And so already in the 80s and definitely in the 90s, there was a trend to change from a multi-bit DAC to a fewer bit DAC.
Yeah, because it's easier to get it linear.
Yeah, let's say if you have just 2 levels,
on and off,
then there is no question about linearity.
No.
But if you have 4 levels, like with 2 bits, well, all the 4 need to have the same type of voltage step to be equivalent. And now the problem is that with digital, the first bit has twice the voltage as the second bit. Yeah. And you can imagine that if you have 16 bits, it becomes smaller and smaller and smaller. And if you have a very tiny voltage here, and really it makes sense to turn it around or turn it on or off or not, then the highest level needs to have the same precision as the smallest level.
Exactly.
And that's the main problem. So then you have a linearity issue. Now, okay, if you don't want it, you have just 1 bit, but 1 bit gives you a lot of noise. Yeah. So we have about minus 93 dB of noise with 16-bit. But with 1 bit, you only have minus 6 dB of noise. So that's way, way, way too much. Yeah. Now, what the solution for that was is called oversampling. Yeah. And it is that you take the original data and you resample that at a very high sample rate. Yeah. And that means you have the sample and then you have lots of zeros because you don't know the information. And then you have the next sample, and you have a lot of zeros, etc. Now the question is, how can you find the intermediate samples, the values of those samples? Because they were not in the original recording. No. Now the way to derive those is by filtering, because if you filter at the frequency that the highest frequency of your original audio, you will automatically interpolate all the zero samples.
All right.
And so then you have the same signal again, but with way more samples. Yeah. Now that has there's no advantage to that, of course, because you have the same information again. Except you have a much higher sample rate now.
But that's how DSD sort of works.
No, not yet, because we have still a lot of bits.
Yeah, true.
But we are running now at a much higher sample rate. Yeah. Now, because we run at a higher sample rate, the noise has already gone down a bit, but not enough. No. So the effect is we have a very high sample rate. The noise is spread out over half of that rate. So let's say we run at 100 kilohertz, then the noise will be spread out from 0 hertz to 50 kilohertz. Yeah. Now, 100 kilohertz is not high enough, so we go even further. So the noise gets spread out to maybe a megahertz or so. But then still the noise in the audio band, that goes down because the average noise is the same as it was, but now
spread out.
0 to 20 kilohertz is only a small fraction of 0 to 1 megahertz.
Exactly.
So we have less noise in the audio band already by the oversampling, but it's still not low enough. and then there's a neat trick that's called noise shaping. Yeah. And that means that the noise that we have in this band can be shaped in such a way that the noise goes down in the audio band and it goes up above the audio band. Yeah. And because of that, you can derive very low noise levels in the audio band, even with very few bits. Yeah. So you don't need the 16-bit anymore. You don't need the 24-bit anymore, because you can push down the noise in the audio band. Now, the question now becomes, how much bits do we need? And in the 90s, the solution was 1 bit. And it was called Bitstream. And we later got it to learn under the name of DSD.
Yeah.
And with 1 bit, you have a lot of noise. So you oversample to a very high frequency. And you have to push the noise down in the audio band a lot. Yeah. And then it goes up above that. Yeah. And the amount that you push it down and push it up, that's the order of the noise shaper.
Yeah, but we all know that filters, a noise shaper is a sort of filter, are very, very important for sound quality.
Yeah, and it's important to understand that what we are filtering here is not the audio.
No, I know.
It's the noise.
It's the noise.
And what is that noise coming from? If you have, let's say, 16 bits, and we throw away 15 of the 16 bits, so we have 1 bit left, the error that we get is the noise.
Yeah.
And so what we don't throw them away and never see them again. No. We use the bits that we threw away of this sample for the next sample, to change the next sample slightly. Yeah. So we are refeeding again and again that noise, but we are only filtering the noise itself. Yeah. So the audio stays the same, but the noise is filtered. Yeah. And
but you have a 11th order, if I remember correctly.
Crazy high amount.
Crazy high amount of filtering. Normally it was like 9.
That's already quite good.
Yeah, 8, 9 is. Why did you choose to make such a steep filter?
Yeah, it's you shouldn't look at it as steep. The advantage is that you have an even more noise suppression in the audio band.
All right.
So you push down the noise more in the audio band.
Yeah.
And then indeed it goes up.
So it's just for the noise floor to go even more down.
Yeah, and you can see that noise floor as the lower noise floor gives you a higher resolution.
Yes.
The less noise in the audio band, the higher resolution in the audio band.
And you don't use 1 bit like Bitstream or DSD.
No.
But you use 1.5 bits.
Right.
And I explained it a little bit in the article. It's like a pulse width modulation technology.
Yeah, but that's 1 bit already also.
Yeah, it is, of course. But you use 1 extra step.
Exactly. Yeah. Because you can use with 1.5 bit, you have 3 options instead of like 2 options for the width of the pulse.
And what is the advantage of that?
The advantage is that with a 1 bit modulator, as this is called, the noise shaper is called a modulator. Yeah. There are the signal, including the high frequency energy, is dependent on the audio signal. So if the audio signal changes, the signal has a different form. Oh, yeah. And what you see, and that's easier to see at the very high frequency part, that you, of course, not here, but it's measurable. Mm-hmm. You can see that changing quite drastically with the audio data. Yeah. There are some examples of that in a
I noticed it in your white paper as well.
Paper, right. Yeah. Now, if that changes at the high frequency side, there's also a little change in the noise floor in the audio band. Mm. And so you get noise modulation, as it's called. Yeah. And we rather not have that. No. Now, the question is how to avoid it. And there's all kinds of ways to avoid it. For all those different options, you always need more than 1 bit. Yeah. And so the question is, how many bits do we need?
Yeah, you want it as little as possible
to get to a solution. Yeah. Now the trouble is that if you add bits, the demands on the processing become larger. Ah. All right. So the more bits you have in your noise shaper, the more processing power you need to do it right.
Yes.
And if we turn that around, if we have a certain amount of processing, the fewer bits we use, the higher the precision becomes.
Exactly, yes.
So that's a trade-off.
Yeah, and you found the
And the optimum was at 1.5 bit.
All right, well, makes sense.
Yeah, so it's just a matter of the question is, can we achieve the noise modulation free performance already with 1.5 bit?
You could.
And we could. So why do more?
Yeah, I totally get it.
Yeah. Strange enough, this technique has been used in analog to digital converter chips already in the 90s.
Oh.
But I haven't seen it much in digital to analog converters.
I didn't know.
No.
All right.
But it's a known technology.
There's one question remaining for me, and then we will have to go to the analog part. Otherwise, we will sit here for 2 hours. We've been here all morning, by the way, but it's been very fascinating. At Alpha Audio, we always want to compare stuff. Online streams versus downloaded streams versus CD versus all kinds. And we always hear a difference. Now, there are, of course, you have to have the same master. So we downloaded a file from Qobuz and we streamed the same file from Qobuz and from the hard drive. And there are actually audible differences. Have you noticed such differences, or have you heard of it? And where do you think this is coming from?
There's a lot to do about this. Many people try to or have their preference over certain file forms and etc.
File formats, of course. Also.
Absolutely. Now, the main message to take home is that if the bits are the same that come out of your computer and go on the journey to the DAC, if the bits are the same, it cannot be a digital problem. So there is no issue with the router giving not the right data or the computer not doing its job.
Bits are bits.
Bits are bits.
End of story.
So when we're looking in the digital domain and we're not doing any format change, like we do with the upsampler in the MU1, for instance. But if you don't do any format change, you can do a very easy test and check if the bits are the same. Now, when the bits are the same, by definition, it can only be an analog problem. Now, analog is everywhere. So analog is in jitter of the clock that does the actual conversion from digital to analog. Because I talked about the modulator, that's still digital. But the modulator is connected to a single flip-flop that does the actual switching. And it has to switch at the right time. So it runs on a clock, and that clock is an oscillator somewhere. But that's an analog signal, that clock, because the flip-flop can switch just too early or just too late. There's nothing digital about clocks. Now, so that's one option. Jitter. That there is some influence on the jitter. But there is much more analog in your system, of course. You have to look further than just the streamer box, because the streamer box is connected to a DAC in the MU1 case, or in the MU2 case, it's connected still to a power amp, and whatever analog equipment is
can influence the performance.
Is also analog. So if there is a path towards that analog device through power supplies, maybe the power supply of the switch causes some interference, maybe it's dependent on whatever the switch is doing, and then there is a path to the amplifier and maybe there is some interference there. Well, this is very tiny signals, of course, but we are quite sensitive in our hearing. But the main thing is, if you know that there is a path, you can start to measure it.
And you can see the interference.
You can see the interference, and that's what you did. You checked power supplies of the various equipment, and there are differences, and those differences influence the analog parts of your system.
Well, I think that answers a very big question for a lot of our readers, including us, by the way. I thank you for your time. This was the digital part of the MU2. Now it's time for the analog part of the MU2. I know we're way over time, but it is what it is. Thank you.
You'll have to edit a bit.
Yes, thanks.